In this video, we're going to talk about geometric gradients as part of our engineering economy unit. So to recap, last time we were talking about arithmetic gradients. So here we have periodic payments that increase or decrease by the same amount each time period. And we'll remember from this lecture that these tend to discount 2 time periods prior to the first occurrence at G. So in this cash flow diagram, G would occur at year 2 and we would discount to year 0. And we remember from how we solved for the present value of arithmetic gradient cash flows is that we broke them into 2 cash flows. One being the uniform distribution starting at end of year 1. So we see $100 per year for these 4 years shown with this 100 times a P given A factor. And we added that to this gradient distribution starting at year 2, which we can see that's 100 plus 25 broken into 100 at year 2 plus $25 at year 2, shown by this $25 times the P given G factor. And in this lecture, we're going to build on our discussion about gradients and talk about geometric gradients. We're going to compare and contrast these types of gradients, and then we're also going to set up problems involving gradients. So what are geometric gradients? So unlike arithmetic gradients, geometric gradients increase or decrease by the same percentage or growth rate each time period. In this cash flow diagram, you'll see that C is considered the initial payment. So if we, for example, said the initial payment was $500 and it increased by 2% each year, then our C would be $500. We see that there's a growth as we move along our timeline here, and our growth is impacted by our R here. R is defined as the annual percentage change or as the growth rate. And then we also have to consider I. So I is our interest rate that we are still interested in as we're growing over time. So our R and our I may be, but are not always equal to each other. And another note about geometric gradients versus arithmetic gradients is that we discount to 1 time period prior to the occurrence of the first payment. So that would be the first occurrence of C. So for example, here, C occurs at year 1. So when we discount it to the present value, it would discount to year 0. So let's look at another example. So like I mentioned, we would discount this gradient series to 1 year before the first occurrence of C. So here C is 7,500. We know that the first occurrence is at year 5. So when we applied the present worth formulas, we would bring it back to year 4. Okay. So let's talk a bit more about what we have on this slide. So we see that we have 4 conditions when we're talking about geometric gradients. We know that when R is greater than I, we'll have a present worth formula compared to C, I, R, and then this new variable, which I'll talk about in a second. We also know that R may be less than I, which is the case in this example up here. So we know that we're growing by 2% per year. So we're putting in an additional 2% on top of our additional 7,500 each year. And then we know that our interest rate or our discounting factor is 5%. And then we may have these 2 values as equal to each other. And finally, we may have n going to infinity. So we're going to talk about each of these cases in detail. So starting with when R is greater than I, and I know that there's a lot of information on the slide, but we'll talk through it. So first, I want to highlight that we have this omega factor, which we're going to treat as our interest rate for some of these values. So you see that we consider R and I as well as this factor omega. And I want to highlight that omega is defined as a relationship between these 2 discounting rates and growth rates. So here, when R is greater than I, omega is equal to 1 plus R divided by 1 plus I minus 1. And the present value can be found by taking that C, or that initial payment value, dividing it by 1 plus the growth rate, and then by this expression here. You may also see this written as the initial payment divided by the interest rate times an F given A. Here again, this would replace your interest rate on the factor tables, and then the number of time periods. When we have R is less than 1, we can calculate omega in a different way. I want to highlight that we calculate omega differently depending on the relationship between our growth rate and our interest rate. And then similarly, we would calculate the present worth in a different way. And if you're interested in seeing the process to get these formulas, the derivations are in the Engineering Economy Reader on pages 52 and 53. And then finally, we have the case where R is equal to I. And so you see that here it's the initial rate times N, so the number of time periods, over 1 plus R. And this is equal to the same expression over 1 plus I, since R is equal to I. Now, there's a special case that we may see sometimes in engineering economy, and we'll just talk about it really briefly. But you see here that when R is greater than I and N goes to infinity, our present worth goes to infinity. So this is not very useful to us in engineering economy. It's not really mathematically meaningful. A similar case happens, I'm going to come back to this in a second, but when R is equal to I, then our present worth over our initial investment also goes to infinity. So there's no net growth or decay, so we would need other methods to calculate meaningful present worth here. But for R is less than I, our series converges to a finite value. So our cash flow growth rate, so R is less than our discounting effect I, and we're able to calculate our present worth as being that initial payment over 1 plus the growth rate times the this calculated interest rate, which is equal to this relationship between the interest rate and the growth rate. And I want to highlight that this is the same that we saw on the last slide for the R is less than I case. So let's talk about a problem to give a better sense of what's going on here. So here we have, we're looking for P, we're given C, we're given R plus 2% per year, and we're given I. So, and this is over N is equal to 40, and we know that we'll discount this value to year 4. And then we'll have to go from year 4 to year 0 to find that present value. So the first thing I want you to look at here is that R is less than I. So that gives us a sense of what is the appropriate equation to use. And there's a note here, don't separate it into 2 parts like we had been doing with the arithmetic gradient. So P is equal to C over 1 plus R times our P given A. This is omega here and our number of years. So we can pull our formula that we saw 2 slides ago, plug everything in. So first we're calculating omega, which is 1.05 over 1.02 minus 1. We get 2.94%. And then we can plug that value in to our present worth equation. Again, this is the present worth at year 4, so it'll become a future worth later. But we have our initial factor, and then we have our 1 plus R, so 1.02, and then we plug in what we get from here for our number of periods. And I want to remind you that even though it says in here that we have actually 36 periods, because there will be 36 payments between year 5 and year 40. So we calculate that and we get 161,979 at year 4. And because we have to bring it back a couple of years, then we apply our P given F formula. And if you go to your factor table, you'll find that the P given F at 5% for 4 years is 0.8227. Multiply that by your original future value, and you get 133,261. If you would like to pause the video and try these problems, I encourage you to, and then you can play the video when you're ready to see the solution. So this problem asks us to first draw a cash flow that starts at end of year 5 with a value of $5,000 and increases each year by 5% at n is equal to infinity. And then considering the problem above with a discount rate of 7%, so I is equal to 7%, which is greater than our R, we're going to calculate the equivalent present value. So the first thing we do is draw our cash flow diagram, and you could have drawn exactly like this, or you could have drawn arrow for P at year 0. But here we're just demonstrating that our first payment starts at end of year 5. We start at $5,000 and we're increasing by R is equal to 5%. And then we know that R is less than I, so we use the formulas given to us earlier. And we're able to calculate our omega is equal to 1.07 divided by 1.05 minus 1, or 1.9%. And so we know that we can use our as n goes to infinity for R is less than I formula. So P is equal to C divided by 1 plus R times omega. And so we can just plug all of our values in, and we get 5,000 divided by 1.05 times 0.019, or our omega here written as a decimal, and we get 250,626.57. And then we know that we're at year 5. This has been discounted to year 4, and now we want to discount it to year 0. So we just apply our present given future formula for 7% and 4 years. So if you go to your factor table, you'll find that that factor is equal to 0.7629. So to recap, we have a few different cases. I wanted to show the summary on the screen here, and I'm going to pause the video here and come back and give you a couple more examples on geometric gradient problems.